What's going on, you bunch of nerds? Today I want to talk about constant voltage systems and how LED COBs work on constant voltage as opposed to constant current. Now, normally I recommend that people go with a constant current driver, especially if they're new to working with LEDs, just because of how simple they are to use. It's much easier with a constant current driver to make sure that your COBs are getting the exact level of current that you need them to. With constant voltage, it's a little less precise, and you're sort of trying to find the right voltage that level of current happens to occur at. But constant voltage does have its merits and advantages. For one, it's a little bit safer. I mean, most of these systems are running down at 36 or 50 volts as opposed to constant current systems, which can be maybe 100, 200, or even 300 volts. And another nice thing about constant voltage is that it's a little bit more expandable. You can continue to add COBs to it as long as you have enough current, whereas with a constant current system you might be maxed out and you can't really add on anymore in series. But unfortunately, there are a lot of misconceptions out there and misinformation about how COBs work on constant voltage. A lot of people seem to think that if they have a driver that does 36 volts and has, say, a max of 5 amps, that driver is putting out 5 amps all the time, and that's not the case. So people think, yeah, I'll throw my COB onto this 5 amp driver and it's going to pull all 5 amps and blow up. But that's not how it works. So I'm going to show you in this video with my meters how it does work, and one other thing I want to show you too is how Meanwell's constant voltage plus constant current drivers work. I know there's a fair bit of confusion out there on how these things function, so hopefully I can clear that up today. Alright, let's get started. So this driver that you see on screen is my new Meanwell HLG 100H36A. It's a CV+CC driver, and it does 2.65 amps at 36 volts. And both of these are adjustable. There are two little potentiometers in the top right that you see, the IO and VO adjust. Voltage is adjustable from, I believe, 33 to 40 volts, and the current is adjustable from 1.65 amps to 2.65 amps. So here's my little test bench. I've got my two Vero 18s side by side with their fans. I've got my multimeter on the right here, and the driver is plugged in and terminated on a little terminal strip here. You can see the red and black on the corner, and I've got a couple little jumpers just to make wiring multiple COBs easier. So first thing I'll do is check the voltage with no load connected. Even though those fans are on, the lights are not connected right now. It's just the driver that's on the terminal block. And as you can see, adjusting the current pot does nothing, but adjusting the voltage turns it up from the minimum, which is 31, all the way up to the max, which is 41.25 here. Next, what I did is turn it down to about 35 volts, which is a reasonable voltage for one of these Vero 18s, and then I'm going to hook up one of the COBs and recheck that voltage. I chose 35 volts because according to the datasheet for these Veros, the suggested drive current is 1170 milliamps, and this happens to occur at 35 volts across the COB. When you're hooking up COBs in parallel, whatever voltage you set the driver to, you can expect to see across each of the COBs, up to a certain point anyway. And the current is what's going to be different between them. This is pretty much the exact opposite of a series connection on a constant current driver. Now that I've got this first COB connected, the voltage is obviously the same as it was when we tested with no load. It's about 35 volts. And I'm going to hook up the next COB as well, and this number shouldn't change. The voltage should remain the same as you keep adding COBs until they try to pull more current than the LED driver can provide. So let's say, as an example, at 35 volts, each of these COBs is pulling 1.2 amps. Two of them combined is 2.4 amps, which is under what this driver is rated for. It's rated for 2.6. But if you try to add another at this voltage and it tries to pull another 1.2 amps, then you've got 3.6 amps total, which is more than the driver can provide. And what it will do is hold its max steady of 2.6 and then lower the voltage to accommodate. So as you can see here, voltage is the same, even with both of these COBs hooked up. It's about 35 volts. So what I want to check on next is to find out exactly how much current is flowing to each one of these COBs. And it should be just about the same between them. This is where IV curves are important. So LEDs are kind of weird. Each of them has their own unique current voltage relationship, and one LED, say at 36 volts, might typically want to pull 1 amp, where another LED at the same voltage of 36 might want maybe 1.4, 1.5 amps. And even LEDs of the same make and model, just like I have here, can have unique curves. I mean, generally they're binned to be as close as possible and as uniform as possible, but there's going to be some variance. What I've done here is switch my multimeter over to current mode, and now I'm checking the current flowing to the first LED, which is about almost 1.2 amps roughly. Now I'll just switch over to the second COB, clamp on, and check current on this guy. And it's pretty close to the same, about 1.23, whereas the other one was 1.18 or so. You can see as it heats up, it starts to draw more current. It's ever slowly increasing, and that's actually one of the biggest dangers of the constant voltage system, is that as these COBs heat up, they draw more and more current, and then that heats them up more, which draws more current, and eventually it just kind of spirals out of control and it can kill the COB. That's called thermal runaway. And you're susceptible to thermal runaway unless you use something like a current limiting resistor or some other type of circuitry. Now what I've done here is put my clamp ammeter across the 2 positive wires that go to the COBs, and I'm going to check with the multimeter just to make sure the voltage is the same, of about 35, which it is, and then start adjusting the voltage pot, which is the black screwdriver. So as I turn the voltage up on the driver, you'll see the current rise pretty quickly on that clamp. It's already above 3 amps total between the 2 COBs, and it's now hit the max of 3.4, 3.5 amps. I can still turn the black screwdriver, like there's still room left on the pot, but you'll notice that the voltage doesn't change because it's being limited by the driver that's putting out max current. And that's how the CV+CC drivers work. It's in constant current mode because it's maxed right now. So it's lowering the max voltage. So once I lower the voltage up to the point where the COBs are no longer pulling 100% current, then you can see the current drop as well and the voltage drop. Now you can also lower the current output here and change that range. So as I drop that, you'll start to see the voltage across the COBs drop as well. So I've brought it all the way down to the minimum on that setting. I can't turn that screwdriver anymore, and then I can take the voltage down a little bit further, and I think at the absolute minimum we're getting maybe 400 milliamps between the two, split between the 2 COBs. My meter goes to sleep on me here, but you can see, yeah, there's about 500 milliamps right now, and the voltage is all the way down to 31.76 volts. So just to bring this back up, I'll take the current up and then adjust the voltage, and you'll see more current start to flow. There it is, maxed again. So that's how these CC+CV or CV+CC drivers work. Is their constant voltage up until the maximum current is reached, and then it starts to vary the voltage. So before I was able to turn it up to maybe 41 volts. Now I was only able to turn it up to just under 36 volts because the current was maxed. Here's another example of how the CV+CC works. So I've got one Cree CXB3590 on here, and I'm going to turn it up all the way. The current is already cranked on the driver. Voltage is very low though, it's 31.76, so we'll turn the voltage up as high as it will go. Okay, so you can see on the clamp that the current is about 3.5 and the voltage is about 39.3 volts roughly. So this is max. Everything is at max right now. That's the full current that driver can supply to this COB, and that's the voltage that it's limiting it to. So what will happen then if I add another CXB 3590 to this? Well, the voltage is going to drop. The current's going to stay the same, but now since there's less current going across each one of the COBs, like 3.5 divided by 2 now is about 1.75 each, then the forward voltage is going to be lower because of their IV curves. So what will the voltage be in this circuit? Let's find out. Again, the current is the same. It's 3.4-ish, 3.5 amps, but the voltage now is about 36.5 volts. And like I say, that's because this thing is in CC mode now, and the COBs are dictating what voltage the driver's producing because of their IV curves. So each one has 1700 milliamps flowing across it. Well, at that particular current, that means there should be 36 point whatever volts flowing across the COB.